Hello, this is Reed Althouse for Dean Zeller's CS201 class, and this is my final project tutorial video, and it consists of two classes, the brick class and the brick interface class, and I'll go over both of them. The brick object class creates a brick object and defines its attributes and a lot of methods actually for it. The attributes for it are x1, y1, z1, x2, y2, z2. These are doubles, and this specifies the x1, the starting and ending coordinates in 3D space of the brick. So, like for example, if you had a brick that went from 0, 0, 0 to 1, 1, 1, that'd just give you the unit cube. And then there's a boolean for has studs, and this tells you whether or not there's studs on the top of the brick. And it also has a color for the color of the brick, and this is a Java auth color, which just specifies the RGB value. So for example, in this default constructor that I don't really use, it constructs a brick that starts at 0, 0, 0 and ends with x2 and z2 at 1, but y2 is at 1.2, because if you want to think in terms of Lego units, a standard 1x1 Lego brick is 5 Lego units in width and length, and 6 Lego units in height. So when you scale that, it's 1 and 1.2. And then you just set the color to white and has studs to true. That just creates a default white brick. And then there's the main constructor. This is the one that actually gets used, and it just lets you pass in all of these values for all 8 of these attributes, and it just sets them sequentially like that. And then for all of these attributes, there's getter and setter methods that allow you to set and get all 8 of these attributes, except get color doesn't really get used. All of the other getter methods are very important. And then there's a toString. This one also doesn't get used, but it's good for testing, and it just prints out all of the attributes, starting at the starting coordinate and ending at the ending coordinate, and with studs if it has studs. So now really getting into the meat and potatoes, you have the drawbrick method. And this drawbrick method just draws the current brick, and the way it does that is it draws each of the 3 faces that you're seeing sequentially. So if you're looking at a cube, you're only going to see 3 faces, because the other 3 faces are at the back and they're obscured, so there's no need to even draw those. And then if it has studs, if has studs is true, it's going to call this draw studs method. So now I'm going to explain what draw face and draw studs does, basically. You need to specify whether it takes in a string for the face, and it needs to specify whether it's the XY face, XZ face, or YZ face, because the XY face is when Z is held constant, the XZ face is where Y is held constant, and the YZ face is where X is held constant, and all these other parameters vary. So how standard draw draws a shape or a polygon, because a face is not going to be rectangular when you try and project it isometrically. 3D to 2D, the rectangle is going to become a parallelogram, technically. So to draw this parallelogram, you need the 4 points that make up the parallelogram. And to do that, I'm using a double X array and a double Y array. And X0, Y0 is the first point, X1, Y1 is the second point, X2, Y2 is the third point, X3, Y3 is the fourth point. And it just goes down and connects them. That's how the standard draw polygon method works. I just pass in those 2 arrays and it draws the shape. And to get that shape, you need to take the coordinate of the point you want, because it's sampling 4 points across from out of the 8 that make up the brick. And I just do all of those and get the x coordinate with isometric x and the y coordinate with isometric y, and I'll explain those later. But once it does that, depending on which face you're selecting, it sets the pen color to the color of the object, which you specified up in the constructor here. It makes a filled polygon of that color, and then it sets the pen color to, I guess this would always be black, and it makes a polygon. It makes a regular polygon that's the same points, so you get kind of a black outline there. And the same thing kind of happens with draw studs. So if you notice in draw brick, it draws all 3 of those faces, and if it has studs, it draws studs, and these studs would go on top. So how it draws the studs is it basically takes the center y. You need a center x, center y, and center z of the ellipse, and that specifies the center of the ellipse in 3D space. And then when you want to draw it, you obviously have to convert that from 3D space into 2D space with isometric x and isometric y. So how it draws the studs is it thinks like, well, how long in the x direction and how long in the z direction is the brick? And it loops through x going from x1 to x2, incrementing by 1. And it also loops through z going from z1 to z2, incrementing by 1. So for like a 4x1 brick, x would go from like 0 up to 3, and z would go from 0 to 1. So it would just be 1. It would just be 0 for z. And so once it iterates through this, kind of like how you would a 2-dimensional array, it sets the center x to x plus 0.5, so that you're right in the middle of that brick, or that kind of grid space, and it does the same for center z. And once it has that center x, center y, and center z, it creates an ellipse with this as the x coordinate, this as the y coordinate of the center, and you also need to specify a semi-major axis and a semi-minor axis. That's just what is the radius on the horizontal direction and what's the radius in the vertical direction. And it turns out that when you project a circle into isometric projection, the horizontal axis is 3 times the length of the vertical axis, which is why I have this 1.5 here and 0.5 here. It's just a big mathematical formula that I worked out. So it draws a filled ellipse there at the center, and this one is black. And then it draws another filled ellipse that's the color of the object at the point center x, center y plus 0.2, center z. So what that does is, because the height of a stud is 0.2, or roughly 0.2, it draws a black one at the bottom, and then whatever color it is, one on the top. So you get kind of like a cylinder. It looks kind of like a cylinder kind of protruding out. And if you look at Lego instruction manuals, that's pretty much how it looks. And then it also copies this ellipse in black for the outline, kind of like it did here with this filled polygon and then the unfilled polygon, filled ellipse and then unfilled ellipse. So it does this, it draws that, looping through all of the z values, looping through all of the x values as well. So that's how you get, for example, like if I run brick interface, it's going to create a base, and it just instantly looped through all of these, all the way down, drawing, I think this is like 32 by 32. So it's drawing all of those studs. This would be like 1,024 studs that it's drawing. And if I want to draw, like for example, like a 4x1, I want to make it red, 255. I'm going to place brick right here. What it did is it looped through the z-axis going from 0 to 1, so just 1, or just 0, and it drew the stud there, and then it went to x equals 1 and drew the stud, and then x equals 2, and then x equals 3 and drew the stud, all the way down. So that's how the stud drawing works and the face drawing works. So that's how a brick is drawn, using all of those methods. And of course, you've noticed isometric x and isometric y being used a lot. All that does is it takes this 3D coordinate, for example, like 0, 0, 0, and it says, what should the x coordinate of this be in two-dimensional space? So the 2D x coordinate. And this x coordinate is not the same as this x coordinate, the 3D x coordinate, because you got to factor in the y coordinate and the z coordinate projected into 2D space. And this is the formula I got for the x-axis and the y-axis and the z-axis being isometrically projected. And you can see kind of the direction that it goes. If I click edit brick here, minus z is that way, plus z is that way, plus x is that way, minus x is that way, and y is of course up and down. So that is just the way the axes go. And you have to project it isometrically through this formula to get you the x-coordinate, and then this formula to get you the y-coordinate. And that is a mathematical formula. It comes out of the linear algebra and kind of the rotation matrix, if you wanted to learn more. The square root of 3 part comes from cosine, and the 1/2 part comes from sine. Because sine of 30 degrees is 1/2, cosine of 30 degrees is square root of 3 over 2. And then you get to the move method. This is a pretty simple one. It just takes in the amount you want it to move and the direction you want to move it in. So you can move it in the x direction, y direction, or z direction. And all it does is it increments the x1 and x2 by the same amount, or y1 or z1 or whatever. So if you, for example, if I take let's just do a 4x1 brick like I had before, and let's place it here. If I want to edit that, I want to move it 3 bricks in the minus x direction. You'll notice it does that. I can do whatever I want. So 3 bricks in the minus x direction. All this is doing is setting amount to -3 and direction equal to x. So it's moving it -3 in the x direction. And then a little more complicated is the rotate clockwise and rotate counterclockwise methods. Rotate clockwise, it records the starting x and z coordinates of the brick, just so that it doesn't get disrupted when we change the values here. What it does is it changes x1, x2, z1, and z2 to be what they would be if you rotated the brick counterclockwise. So, for example, what you need to do here is select an axis of rotation. So if I wanted to rotate it like that, I want to rotate it about this stud, and you'll notice rotating it counterclockwise. All that is doing is it's calling this rotate clockwise method, and distance x and distance z specify how far away from x1 and how far away from z1 is the axis of rotation. So for the way I had it, it would probably be 0.5 in both directions. And it's always going to be something 0.5 just so that it aligns with the grid spacing and nothing gets messed up or drawn incorrectly or anything. So that's basically all of the methods to move it, and these formulas, you just get it from, it's math. I did this in Desmos, figured this out. It's not too hard to come up with this yourself. And then I'll get into some Boolean test methods to like compare two bricks and then also to draw multiple bricks. So to compare multiple bricks, you have a couple overlaps methods: overlaps X, Y, and Z, and then overlaps. And then you have an is behind method. So what overlaps X, Y, and Z does is it takes in another brick to compare them, and what it does is it asks, like, do their X coordinates overlap? And they overlap when this brick starts before the other one ends, or the other one ends before this one, or this one ends before the other one, after the other one starts. So that's the formula. Like if you had, for example, one brick going from 0 to 2 and the other brick going from 1 to 3, they would overlap in the X direction. And the same is true for the Y direction. The only thing that's different is X changes to Y, and then X changes to Z here. And for overlaps, this is the important one. This actually tells you whether two bricks occupy the same space, because you can have two bricks that are just stacked on top of each other, and they would have the same X coordinates. They would overlap in the X direction, and they'd have the same Z coordinates. They'd overlap in the Z direction, but the Y coordinates would be different. So it's perfectly valid. You can have that. They can overlap in every direction except the Y direction, and that's still fine. So in order for two bricks to overlap, and this would make it not possible to draw, because obviously two solids can't occupy the same space. It needs to overlap X and overlap Y and overlap Z. So that's just the overlaps method, and that's important for determining, for example, if you're moving a brick. I can show you here. If you're moving a brick, let me just put two bricks down here. Let me put one brick here and one brick here. If I wanted to move this brick, I can move it however much I want in any direction until I run up against this one. Cannot move brick overlaps, because here they would occupy the same space. They would overlap in all three axes, and this is not allowed. But if I moved it 2 spaces, now it's fine again because it just jumped over. So the next thing that it needs to figure out when comparing two bricks is which one is behind the other one. Now obviously you can have two bricks that are like incredibly far apart and that don't even overlap at all, or don't even look like they overlap, and it wouldn't matter. But when you have two bricks that are supposed to, where one of them is supposed to come in front of the other one, because part of it's going to get blocked by the brick in front, the code needs to know that. So the method to determine if this brick is behind brick B is if its X coordinate is less than or equal to the X1 coordinate, or if Y2 is less than B's Y1 coordinate. Basically, if the X intervals are completely apart, or Y intervals are completely apart, or the Z intervals are completely apart. In that case, then you do need to draw brick 2, then you do need to draw this brick before brick B. And in the list of bricks that we have here, if you go into brick interface, you have a static array list called bricks, and this stores every single brick in the project, or every single brick that you want to put gets added to that list, and you need to be able to sort it by which ones come first, or which ones should be drawn first, and which ones should be drawn last, because the ones behind should be drawn first and the ones in front should be drawn last, so that everything looks right. And to do that, we have to sort the array of bricks, but we'll get to this later. First, let's look at the draw bricks method. The draw bricks method is basically draw brick, because you can see it calls draw brick here, but it does it for all bricks in the array. So first what it does is it actually sorts the array. This topological sort method takes in the array of bricks and it outputs another array that's sorted, another array list that's sorted. It returns sorted. So it sorts that and it sets bricks equal to the sorted array or sorted array list. And this enable double buffering just means that until I call the show method, it's not going to show anything, that any of the changes that it's making or any of the drawing that it's doing behind the scenes. So I first clear the canvas completely and then draw every brick sequentially. For brick in bricks, it just draws it. And that's why it was important to sort it beforehand, because if I place a brick on top of the base, for example, like if I do 1, 1, I make it red. If I draw this brick on top of the base, I can do that as much as I want, and the base still needs to be drawn first. If I draw the base after any of these, you're just not going to see it because it's going to come behind. And I can also put one behind here, and you'll notice that the YZ face of that brick that I just placed behind doesn't actually show up. You don't see that because the brick in front of it is occluding it, because I drew the brick in front after I drew the brick behind. So that's why that's necessary. So how does it sort the array? I'm going to be honest, there's a lot of this that I don't understand, but I can kind of go through the logic of it. ChatGPT kind of helped with that. This is an implementation of what's called Kahn's algorithm to topological sort this array, and it basically maps every brick to a list of bricks called graph, and this list it maps each brick to an array list of bricks that basically hold every single brick that should go in front of this brick. It links each brick to a list of bricks in front of it. And this one, called InDegree, maps each brick to an integer, which is the number of bricks that are behind it. So how it initializes this is it takes every brick and it puts them into their own kind of node in the graph, and it gives them each an empty array list. And it also puts their InDegree to 0. So now you have a bunch of nodes that are unconnected of bricks, and we're going to add some connections here to this graph and the InDegree. So we're comparing every single pair of bricks. So if I clicked on the screen 10 times and I drew 10 bricks, in addition to the base, it would go through all 11 bricks and then all 11 bricks again, and it would compare all of them. And obviously, if you compare the same brick to itself, then there's no node you need to add. You don't need to add a connection there. But if B is behind C and C is not behind B, that's just a failsafe to make sure that you don't have any false positives or false negatives or anything. It's going to take B's array list of bricks that it's in front of bricks that are in front of it, and add C. So if B is behind C, that means C has to come in front of B. And so we have in the array list of bricks that's in front of B, we need to add C because obviously C is in front of B. And then also, since B is behind C, we need to increase the number of bricks that's behind C. So InDegree of C needs to increase by 1. And we do this for every single combination, so we have a complete graph and a complete list of every single connection between bricks, or every single dependency where one brick needs to come either in front of or behind another brick. So then it creates a queue for the order that bricks are to be drawn, and this queue is basically first in, first out. So if I add a brick B and then I poll the queue, this just pushes the first brick out of the queue. So these first ones that I add are the first ones to come out. That's how queues work. So if the in degree is 0, that means we've compared it to every single brick and we've found no bricks that are behind it. And this would only be the case for the base, I guess. So we've looked through every single possible combination and there are no bricks that are behind B. That means we can just draw B and there won't be any repercussions. So we add B to the queue. Then, since we've added B to the queue and there's no repercussions to drawing B, we can just add it to the sorted list, and B can be drawn first. Then what it does is for brick C in graph.getB, so that means for every brick that's in front of B, we need to reduce its in degree by 1, meaning now B has been added to the array list, so it can basically just disappear. And since we've already kind of drawn that, any brick that only had the base behind it is also now safe to draw. So that's why we're decreasing the in degree by 1, and we're repeating the process of, let's say brick C's in degree was 1. We subtract 1, now it's 0, because the base was the only brick that had to be drawn before. So now we can actually add it to the queue, and we can just draw it without any repercussions again. And we do this over and over and over again until we've added every single brick to the list, which would mean the queue is empty. And then we have a sorted list of bricks where every brick is in front in the list of the bricks that is behind. So I know I explained that very terribly, but I don't completely understand it myself, and I definitely can't explain it to somebody else, but that's kind of the gist of how it works. That just sorts the list, and then it draws it here. Then we get connected to, and what this does is it makes sure, so the topological sort here made sure that no bricks are being drawn out of their proper place. The overlaps method made sure that no bricks occupied the same space. This connected to method, and has connection here, makes sure that no bricks are floating, basically, or that every single brick is connected validly with studs to every other brick. For example, if I wanted to run this, and I wanted to create like 5x2, I guess, I wanted to place it like here, and then one on top, and then one on top, I obviously can't get rid of these two bottom ones, because then this one on top would be floating. You can't have that in Lego. So if I do remove brick here, I can remove this one. That works fine. But I can't remove this one. It won't let me because cannot remove brick is floating. Then when I click on this one, I can remove it. Brick removed successfully. And then there's also a failsafe where I can't remove the base, but we'll get to that later. Essentially, connected to just tells you, is there a valid stud connection between this brick and brick B? So if brick B was the base and I added something to the base, it asks, is this connected to the base? And the answer would be yes, so this would return true. And the way it does that is, well, first they have to overlap in the x direction and the z direction. And what needs to happen is either this brick is directly on top of brick B, or brick B is directly on top of this brick. And for it to be directly on top, the y1 coordinate has to be equal to the y2 coordinate of the other brick. So if y1 equals b.get y2, that means that this brick is on top of B, like completely. And also, B has to have studs so that there's a valid stud connection. And then the other way goes as well, where if B is on top of this brick needs to have studs. So that's the condition that tells you whether two bricks have a valid connection. And it also lets me do something like this, where I have like a hanging brick, kind of. Let me try and demonstrate that. This was kind of the problem I had that led to the creation of this method. Let's say I wanted to put a brick here. If I wanted to like kind of slide that, let's do edit brick and let's move it out here. Let's move it. Oops, wrong brick. Let me click on the brick I want to move. Let me move it back here and here. Right. So now, if I get rid of these, we have this brick that's kind of hanging off of the edge. Now, technically, it is floating, but since it has a valid connection with the brick above it, and the brick above it has a valid connection with the brick below it, and that has a connection with the brick below it, and that has a connection to the base, basically, it all has to come back to the base. You have to find some sequence of connections that lead to the base, or else it's not valid. Which is why if I wanted to remove this top brick, because this brick is contingent on that, it won't let me remove it, because cannot remove brick is floating. It would leave this brick floating, and that can't happen. Well, I've actually never tested that, so I'm really glad that worked. But how that works is has connection takes in a list of bricks, and it asks, given this list of bricks, does this brick have a valid connection with the base, essentially? And it assumes that the brick list is sorted. And now I'm going to kind of get into how this algorithm works, because this one I made myself, so I can kind of explain it better. It uses this connected to method to determine whether this brick basically is floating or not. Should exist, because if it's floating, then, I mean, it shouldn't really be there, and that's a problem that the brick interface needs to address. So what it does is it defines like the brick base to be the first one in the list, which is why it needs to be sorted beforehand. And obviously, if this brick is the base, it's going to return true because the base doesn't need to be connected to anything. But then we need to say, is this brick connected to the base? And if that's true, we return true. So what I do is, for brick B in bricks, we want to say if it's connected to B. And if it is connected to B, if B is the base, return true, because any brick that's directly connected to the base is good. Or if it's connected to something that's not the base, then we need to ask, is that brick connected to the base? Or is that brick connected to something that's connected to the base? Because if it's connected with something that has a valid connection, then it also has a valid connection. So what I did is I made a copy of the list of bricks just without this brick. I removed this brick just to avoid like infinite sequence where, like, if you have two bricks that are connected and they're both floating, it'd say that brick's connected to this brick and then this brick connected to that brick and so on forever. We'd get probably a Stack Overflow error in my testing. So I had to remove this from the list, from the copy of the list. And then I pass list copy into has connection. So now it's the list of bricks without this. And if that brick that we know is connected to, if that brick has a valid connection, then return true. So until we hit the base, until we get to a brick that equals the base, or if we get to a brick that's connected to the base, it's going to keep on going. And if if we go down like a path, if like let's say a brick is connected with two other bricks, and the first one of those bricks is not connected validly, then this is never going to return true. And that's why I put this all in a for loop, so that if B basically leads to a dead end, it can keep going and it can keep searching for other bricks B that's connected to it and basically tell you if that one has a valid connection. And if it goes through the entire list of bricks and finds no brick whatsoever that is both connected to this brick and has a valid connection with the base, then it's going to return false. And if it returns false, then we have problems because we've left a brick floating, and we can't do that. So the user has probably deleted a block that can't be deleted. So that's the has connection method. I'm pretty proud of that one. I used zero ChatGPT on that. And then we have a couple is clicked methods, just to round out this way too long class. 583 lines is absurd. And also rounding out the first half of this video, which is also way too long. The is clicked YZ, XY, and XZ methods basically is a mathematical formula. It gets the mouse X and mouse Y of the cursor. So if I run this code, if I run the brick interface, if I put my mouse here and I click, it's going to standard draw is going to calculate where my mouse should be, where the mouse coordinates are in relation with the canvas. So if I put it like probably about here, that's close to 0, 0. So it would do mouse X is 0 and mouse Y is 0. That's all handled for me by standard draw, which is really nice. All I need to do is pass that into this method, and it's going to say, it's going to do these mathematical formulas, because if you remember, the YZ face is the one where X is held constant. So we're going to have a constant X that's just X2. And then we're going to use that along with mouse X and mouse Y to calculate what the Z and Y coordinates, the 3D coordinates, would be if this mouse lied on that plane, the X2 plane. So it's really, these methods are really isometric X and isometric Y in reverse. That's how I thought of that when I was mathematically coming up with these formulas. It basically says, the gist is if you took X, Y, and Z and did isometric X on it, your X and Y coordinates should lie on that face if the mouse is truly clicking that face, which is why once you find the Y and the Z value, you need to say you need to return true if the Y value you get is between Y1 and Y2 and the Z value you get is between Z1 and Z2. So, for example, if I clicked on the YZ face of this brick, let me just place one here. I'm going to click on the YZ face. This is the x-axis. The YZ face is this one. It knows I clicked on that. But if I clicked on here, it knows I didn't click on that, which is why it's going to place another brick, because if I clicked on this plane, if you can imagine this face just extending forever in both directions, the spot on that plane I'm clicking on does not lie within this tiny square here, which is why it doesn't let me do that. And the same goes with XY and XZ. These are both just mathematically derived from, again, a system of equations with isometric X and isometric Y all the way up here. These are probably the two most important methods that I wrote for this class. And then finally we have, similar to overlaps where there's X, Y, and Z and then a total, this is face clicked. It returns a string of if it's clicked in the XY direction, return XY, and so on and so on. But if not, then return none. And the main reason this is used is so that I can say if face clicked is not none, then you know you've clicked on the brick. But these individual methods are sometimes useful as well for determining where exactly to put another brick, or I used isClickedXZ in brick interface a lot for other purposes that I'll get to later. So on to the brick interface class finally. Interface class uses this javax.swing library that you have to import, and it creates a brick interface class that extends JFrame, which is part of Swing. And JFrame contains all of the different attributes like JPanels, JTextFields, JLabels, JButtons, and like JComboBox that I'm going to use in this interface. It's got a bunch of variables here, and that just stores the current value of everything that you're looking at. Well, first it initializes an interface panel, and that's the main panel that launches when you press run on this. It launches the interface panel. And then it creates an array list called bricks, which is the array list that you see in this method, in this method, in the drawing method, in that. This is what's getting passed into that whenever that happens, whenever it draws all of the bricks. And then it stores current width, length, height, color, has studs, and also current brick. So if I clicked on a brick in the project in like edit brick mode or anything, it would put that brick as the current brick, just so it knows what brick is being referred to. And then there's also mouse X, mouse Y, and that gets set by the standard draw mouse X and mouse Y methods. And then finally there's 3 modes. There's isPlace mode, isEdit mode, and isRemove mode. And that basically tells you which one of these 3 buttons, place brick, edit brick, and remove brick, should be active. So if I hit place brick, it's now in place mode. Place mode is true, edit mode's false, remove mode is false. If I hit edit brick, now place brick mode is false, edit mode is true, remove is false, and so on. You get the picture. And all that does is whenever I click any of these bricks, any of those buttons, it puts one of them to true and the other one's to false. But we'll get to that. So this brick interface method is the default constructor for the brick interface. It's what is being called in the main method when I want to create a brick interface. All it does is it sets the title of the window to Brick Builder, which you could see, and it sets the size in number of pixels, default close operation, location. That I got from someone else's video tutorial for like their project, their GUI. That's all of this stuff. The real thick of it is in the initialize interface panel method, and that gets called up here. So whenever you create a new brick interface, it's going to do all of these, which means it's going to call this method, and this is where everything is. This is where all the elements are and everything they do. So the first panel in the interface panel is the input panel, and this is this thing up at the top with brick type, length, width, and so on. And with panels, you can choose a layout that you want. And I use 3 different kinds of layouts here. The interface panel is a border layout, which means you can set the location of things, components, relative to the border. So you can set things to the north side, south side, west side, east side, and center of this interface panel. But what I did with the input panel is I made it a grid layout with 7 rows and 2 columns. And as you can see, here there's 2 columns, 1, 2, 3, 4, 5, 6, 7 rows. And in each slot in the grid layout, you can put an element. And here I put JLabels and text fields and combo box and buttons. And you need to make sure you add them in the right way. It adds left to right and top to bottom. So I did brick type label, brick type box, brick length label, brick length field, brick width label, brick width field, and so on and so on. And the very last thing you'll notice is the set brick button, which is this thing at the very bottom, set brick. That should give me an error, but you also need to code when you create a JLabel, you can set the text of the JLabel. That's really easy. JComboBox actually takes in a string array of brick, plate, and tile. I don't think I demonstrated that, but this is a combo box, brick, plate, and tile. If I added another thing like brick number 2 or something, that would also be an option. Yeah, now there's 4 options. That's just how combo boxes work. Let me make that normal. You also then have to set the code for all of these. Now the JLabels and the JText fields don't really change. The label is always going to say that thing, and the text field is always going to be just a blank field where you can put in text. The set brick button, though, you need to actually add an action listener, and an action listener just says, when you press the button, execute this code. This is the code that gets executed when you hit the set brick button. And all it does is, if brick type box is 0, that means if it's a brick, set the current height to 1.2, but plates and tiles have a height of 0.4, so I did that. Then also current width, current length is integer parse int brick width field and brick length field. That just gets the text that you put in and it converts it to an integer. So that's how you tell what the current width and length is. And also the color. The way you declare a color is you give it the red and the green and the blue, and it creates a color object out of that. And also, if the brick type is 2, that means it's a tile. Then it doesn't have studs because there's no studs on tiles. But otherwise, it does have studs. Bricks and plates have studs. So that makes it true. And then also you set the output label, which is this one next to set brick. Next to set brick, it says press set brick to set attributes. When I do that, it says brick set successfully right there. The next panel that it creates is the button panel. Oh, and I should say you also need to add it to the interface panel. I said border layout.north because it's at the top, so it's at the north side of the interface panel. But then on the south side, you'll notice the button panel, and the button panel is pretty simple. It just has 3 buttons: place brick, edit brick, and remove brick. So that was really easy. You just got to add them all to the button panel and then add the button panel to the interface panel. And that's in the border layout south position. Those buttons don't actually do anything yet because we need to add an action listener for all of those, and we'll do that later on in the code. The third panel, though, that you don't see right away is the move brick panel. That doesn't get added to interface panel right away because you need to press the edit brick button for it to pop up, but this is the move brick panel. So when you when you show that move brick panel, you also need all of those buttons in the text field that you see there. So there's the plus X, minus X, plus C, minus C, and then the clockwise and the counterclockwise button. Those are just Unicode characters for rotating arrows and that. And then there's the move amount field. You also need to add those components to the Move Brick panel like that. But the thing with the Move Brick panel is I used a spring layout. So we've gone over border layout and we've gone over grid layout. Spring layout is very complicated. I used like an outside resource to figure out how spring layouts work, but it deals with put constraint right here. So the spring layout object is this thing right here, and I set the layout to that spring layout. But what you need to do to say where all of the components should go in spring layout, because grid layout handles that for you, border layout handles that for you. Spring layout, you need to manually say where you want all of those buttons to be. For example, the move -Z button, I wanted it to be on the top left corner of this panel. So to do that, I put a constraint that says the west edge of the -Z button should be offset, which is 50. I said offset equals 50 there. Should be 50 pixels from the west edge of the Move Brick panel. So that just specifies the distance. So that means the distance between this edge and that edge of the brick of the panel, that distance is 50 pixels. And I did that with the north edge of the button should be 50 pixels from the north edge. Same thing with the positive X button, and I actually put it to south. And minus offset just means instead of 50 pixels down, it's 50 pixels up, or instead of 50 pixels left, it's 50 pixels right. And I did that with all those buttons. And then the rotate clockwise and counterclockwise buttons, I set them in relation to the horizontal and vertical center of the panel instead of the edge. But the same principle applies. It just means the horizontal center of the rotate clockwise button should be 25 pixels away from the horizontal center of Move Brick panel. And I do that a bunch of times to specify where those buttons and that field and that label should be. It looks like a lot, but it's pretty simple, pretty straightforward. And then you need to add the action listener for all of those. And that's a little more complicated. This is where the logic of the interface really goes. This is where the brick interface actually talks to the brick class and back and forth and everything. So I'll try to explain that. Okay, so the -Z button, or the -X button, or the positive X button, and so on, all they do is they call the move method of the brick class, this method right here. And the real trick for that is making sure that you actually can move it. For example, if I tried to move a brick to where another brick is, it's not going to let you because it overlaps. So the amount that you want it to move, you get it from the move amount field, obviously. And for -Z, because it's negative, this is negative amount, and it's in the Z direction. The only difference between the 4 action listeners for the move buttons is this, whether amount's positive or negative, and whether direction's X or Z. To check if the new brick overlaps, makes anything overlap, I set a Boolean overlaps to false, and loops through the list of bricks and say, does it overlap the current brick? And if it does, then overlaps is true, and you can't have that. But if you've gone through the list of bricks and none of them overlap this one, then you're fine. But if overlaps, we're going to move it back. So it used to be negative amount in the Z direction, now it's positive amount in the Z direction, just to undo what we've just done. And then it sets message label can't move, brick overlaps. But if it doesn't overlap, then we need to check, is everything connected? So I do the same thing, Boolean connected equals true, and then I loop through the bricks, and if there is no connection with the bricks, then I set connection to be false. And that can't happen, which is why I say if not connected, then cannot move, brick is floating, and then we undo what we just did. But if it doesn't overlap and it is connected, so if overlaps is false and if connected is true, we have an else here that says message label brick moved successfully, because we've already moved it up here. We're done. It just works. And that's the exact same code, and then afterwards we draw the bricks. And that's the exact same code for the move negative x, and it's the same thing for move positive z, and it's the same thing for move positive x. The only difference is we're moving it positive amount in the x direction, and when we want to reverse it, it's the negative amount in the x direction. But the code is essentially the same. Then we get to rotate clockwise and rotate counterclockwise. This one's a little more complicated because you need to ask, where is the axis of rotation? So if current brick is clicked, we need to ask if the current brick is clicked with mouse X and mouse Y. This code is basically copied from the XZ method. If you look at the isClickedXZ down here, these formulas right here are the exact same as these formulas right here, except it's mouse X and mouse Y, and current brick instead of this. And then it says the distance is floor of x plus 0.5 minus current brick dot get x1. So that just says the x coordinate that you've clicked, we're going to center that in the nearest block. So it's to the nearest 0.5. And the same thing with the z. And we take that coordinate and we subtract the x1 to get the distance from x1. So you have 2 points and you subtract them to get the distance, basically. Then and only then we're ready to call the rotate clockwise method for distance x and distance z. Then we need to do the same checks with overlap and with connected. And this is the exact same code as from before, where if it overlaps, then overlaps is true. And if overlaps is true, then we actually recalculate the distance x and distance z. This is copied and pasted from up there. And we rotate it counterclockwise. So this is just the same way from before of undoing what we've done. And it says cannot rotate, brick overlaps. And then connected is the same, and cannot move, brick is floating. And we rotate it counterclockwise to undo what we've done. So it's the same principle as these buttons, a little more complicated because of how the counterclockwise and clockwise method works. But the operating principle is kind of the same. And if it's, and then we draw bricks. But all of this code was inside the if current brick is clicked. If it's not clicked, then we say cannot rotate, click on rotation axis, because then it just doesn't know where to rotate it around, and it wouldn't be possible to rotate it. So we're just going to display that message and not even worry about rotating it. And the same thing goes for counterclockwise. It's copied and pasted, except instead of CW, it's CCW, and then instead of CCW, it's CW. Everything else is the exact same. Then the place brick button has an action listener. And the action listener for place brick, edit brick, and rotate brick are kind of similar. They're basically the same. So first I say output label.setText, click on brick viewer to place brick. That's just the prompt message there. And I set edit mode to false, remove mode to false, and is place mode to true. Then I remove the move brick panel if it exists, because we don't want it to show up. If you remember, the move brick panel only appears when you're in edit mode, and this revalidate and repaint just makes sure that all of the components in the panel are there. It basically clears everything and puts it on again. Then we need a new thread. This part's kind of confusing. I had to use AI for this part too. But all of this code is inside the new thread, everything here. So this is basically a method that's executed when that button is pressed, and it's a while loop. And the reason why this while loop needs to be in the thread is because if you never exit place mode, this is just gonna execute forever and ever and ever and ever and ever. So you're never gonna get the chance to get out of place mode. So this is just gonna keep on executing, which is why we need a new thread so that it can run in the background and we still have the opportunity to press other buttons and do other stuff and run other calculations and everything. That's why this needs to be separated into its own thread. And then at the end of the thread, we have to do .start so that this process can begin, I guess. So the thread says while we're in is place mode, we're gonna look for if the mouse is pressed, and this method just comes from standard draw. And then I say while standard draw is mouse pressed, and this while loop is empty because we want it to do nothing until you release the mouse. Once you release the mouse, this while loop is going to end, and we're going to get the mouse X and mouse Y. And we're going to set that to mouse X and mouse Y. Then I make a new array list for all of the bricks that we've clicked, and we just run through the list and say, if it's clicked, then add it to this list. Then, this is probably a little janky and I could definitely make this better, but we loop through the bricks array list in reverse. We look for the last element and then the next last and then the next last, just so that we get the one at the very front. Because if you're clicking on something, if you're clicking on two bricks at the same time, the one you really mean to click is the one that you're seeing, is the one that's in the front. So if clicked contains that, meaning in the list of bricks that you've clicked, if this brick is in there, then I do this code again. It's the same exact formula as the is clicked, and I set that to be the y, x, and z coordinates. And I make a new brick, because it's place brick, you're creating a new brick with the x coordinate of the floor of x, y the floor of z, and then floor of x plus length, y plus height, and z plus width, just so it's the correct length, height, and width. And we also say current has studs and current color. And if you remember these two, all of these current variables were set by the setBrick method, and that's so that the place brick button knows how to create the brick object. So that just initializes all those variables. And then we need to do another check for if it overlaps, same as before, and if it overlaps, we can't place it. Otherwise, if the brick you're placing it on has studs, then you can't place brick on tile. So it just won't let you. If it doesn't have studs, it won't let you place it, because you need to place a brick on another brick that has studs. And then else, if it doesn't overlap and it does have studs, that probably just could have been an else. I don't know why I did that, but it sets the current brick to B, and it adds it to the list of bricks, and it says brick placed successfully. And then now that we've added it to the list of bricks, we're going to draw the bricks again. We're going to draw bricks and pass in that array list, and that's going to handle everything behind the scenes of drawing the bricks right from the bricks class. And then we break out of the while loop, or we break out of the if statement. And that means it's going to go back to this, and it's going to look for if we press the mouse again, so that we can repeat the process over and over and over again. And that's the place brick button. And you'll notice that the edit brick button and the remove brick button, this part looks very similar because it's basically the same. The only difference is now interface panel, we need to add move brick panel, whereas in this one we removed it. So same thing goes where we're making a new thread, but instead of is place mode, we're looking for while we're in edit mode. Same thing again with standard draw as mouse pressed. While it's pressed, do nothing, and then we're getting the mouse X and Y coordinates, creating the clicked array, adding it if it's clicked, and same thing, but the difference is now current brick equals bricks.getI. That's all we need to do, is change the current brick to the brick that we've clicked on. And then all the other buttons, the rotate and the move buttons, can handle that because we're doing everything based on the current brick. So that's the only thing that the edit brick button needs to do. The remove brick button is a little more complicated, but it's similar to the place brick button. Same thing again. We're removing the move brick panel, and we're setting all of these ones to false and is remove mode to true. While is remove mode, we do the same thing where we're looking for a mouse input, and we do mouse X and mouse Y, create the clicked array, same thing. This one, I did find a better way of doing it, where you just sort the array of clicked, and then you get the last one. Brick removed equals click.getLast, because we want the one in the front. Now, if removed, which is this last one that you're clicking on, this is the one that you've clicked that you want to remove. If removed equals bricks.getFirst, you can't remove the base, because bricks.getFirst, this first one in the list of bricks, is always going to be the base because it's behind everything else. But otherwise, we're going to remove it from the list of bricks, temporarily at least. Then we check for it being connected, and if it's not connected, add it back in. Same thing with the move buttons and the rotate buttons, everything like that. Otherwise, we're going to say brick removed successfully, because floating is the only thing we need to check. Overlapping is never going to happen. And then we draw the bricks and start the thread, just like the other ones, just like the place brick and edit brick. Everything happens inside the thread, and that is it for the initialize interface panel. Then the last thing in the brick interface and the program is the main method. This is what's executed when you hit run. And it does standard draw.set title brick viewer, so it creates the standard draw window right there. And it sets the X scale and the Y scale and the canvas size to what we want. And that's also important so that we get the right values for the mouse input. Then it creates the base brick. And I set the base half length to 16 so that it becomes a 32 by 32 base, which is what you'd see when you buy a Lego brick, buy a Lego base plate. And then it adds base to bricks, pretty simple, and then it draws it. So the only brick that's going to be drawn is the base. And then it calls new brick interface, and that is going to go all the way up here and execute this bit of code, which inside of it is initialize interface panel. That's going to execute all of this code, and that's going to make everything start working. And that's the last thing that the main method needs to do, and indeed the project. So that's it for the brick interface and the project. This took me a lot of effort and work, and the video is probably way too long. I think we're going on an hour. I'm going to need to speed this up. But thank you for listening, if indeed you have. And have a good day.